So this came about from a lot of multi-billion-dollar ports being proposed on the West Coast, and it appeared we didn't have sort of, as experts in a number of different fields, we didn't have guidelines designed to scientifically make decisions in some cases. Next slide. I'll skip past the abstract, but it's all there for people that want to see. It's a very small project with big implications. So basically, Environment Canada are funding this project. I'm the expert in sediment dynamics, and together, by producing these guidelines, we've affected probably $60 billion worth of infrastructure and helped to either, allow or not allow that. Next slide, please. I think in the interest of time, I'll just skip to the next slide. Thank you. The issue is that there's ports being designed all the way up and down the west coast of Canada. There are only certain dredge disposal sites available, and every port project, every coastal project basically requires dredging. And you can see that in the center part of British Columbia, there are no dredge disposal sites, and that's where a lot of these infrastructure projects are being proposed. So it costs the proponents a lot of money when they have to spend several years transporting sediment or construction wastes from their location to these disposal sites. And it can be in the tens of millions of dollars in transport and also in reduced, time to get to a functioning port. There were a number of licenses in, and it was clear to us that guidelines were required on how to dispose of sediment and what's the sites, how do we assess the sites of whether sediment will be dispersed and what type of contaminants can be deposited there. Next slide. Here's an example that I'll follow through with the rest of the talk here. This is a port that was being proposed off the north coast of BC. The dredge disposal site here is about 50 miles away, so they wanted to propose a disposal site here right off of where they were going to do the dredging. And in this case, we got some early modeling a few years ago that was based on data collected in the summer of 1992 or something, and they used that to calibrate their model to give an idea of this dispersion. But this is obviously the model produced a north-south dispersion, but based on knowing the area, I knew that in winter there would be storm surge in a west-east direction and then a sort of backwash from the storm surge in a east-west direction. So it was clear that we had to not rely on the model, but to actually go out and measure dispersive characteristics of this site. Next slide. And we did that through several methods, and we're continuing to develop these methods into the guidelines. One is to use bathymetry on the left-hand side. You can see it's a fairly flat bottom there, so we don't see any erosive troughs or mounds of deposition in that sort of orange flat zone. On the right, though, we do see from the backscatter from our ship-based instruments that there's more sort of sand in the northern area, and the darker stripes indicate mud. So that tells us that that site near the bottom there is non-dispersive. Generally, it's sort of mud being deposited there as opposed to high currents and sand. Next slide. And we can also use coring and lead-210 analysis to give us depositional rates, and we've done that for this area. So next slide. The sort of point I'm making is we can do a huge, big research project. We can, but proponents might not necessarily be able to. So we're trying to come up with guidelines for dispersivity that don't require 10 different types of scientific expertise, and I'll get to that. So there's hydrodynamic modeling, which I showed in a previous slide. Next slide. So we're going out and deploying instruments to determine what's the simplest, most cost-effective way for us to get a kind of a criteria for determining whether a site is dispersive or non-dispersive and in what direction. And on this slide, you see that blue and red instrument is an acoustic Doppler profiler, so that's measuring currents profile throughout the water column. And that cannon-shaped sort of thing is a turbidity sensor that is in that protective kind of cannon close to the bottom. And so by doing this, we're measuring currents and suspended sediment from the bottom. Next slide. It's a very expensive kind of, requires world-class scientific ships to do this work. So we're trying to hone it down to what a consultant would be able to do with a small vessel. And the next slide. So the guidelines we've come up with so far follow some that the U.S. Army Corps of Engineers used. We've modified it a bit, and this is that we use a peak current speed, in this case 25 centimeters per second, and say, okay, if most of the currents fall below that, we're going to call this site non-dispersive, and you can dispose of different types of material than if it was dispersive. And in this case, this was a deployment a couple of years ago where only one of the measurements out of a whole month reached that peak, yet that was almost enough to take it up to the 25 centimeters per second. So it's a fairly, I guess, conservative approach that we say rarely ever should the currents exceed this velocity, and then we'll call it non-dispersive. And one more slide. So that's what we're using as a very simple definition, and this guidelines is now handed out to different proponents who are proposing dredge disposal sites, but we're doing further research on the resuspension, turbidity, and transport of sediment to determine if that guideline is actually the best way to go. At the time, we were kind of under pressure of basically delaying multiple port projects, and we were under a lot of pressure to come up with some guidelines, and we did, and we think they're robust, but we're now measuring, as in this, concentration of sediment being transported in the water column versus current speed to determine if our threshold is reasonable. And that's it. So Environment Canada, we're assessing all of the existing sites, and any new sites will be dependent on the proponent to use our techniques.
Thank you, Gwyn.